Answer a quick question.
Sure.
Okay. So, it says like to replace 0 on, let's say, the first integral or the second derivative. So if you do the first derivative here, this goes to 0 and it becomes 3, but minus 3, right?
Yeah, this is just the power.
Yeah.
Derivative,
So
right?
when, I don't know why, like when I check the answers, it's like in the first, with the, this one is the first derivative. This one is the first, right?
So this is where we discard everything that has degree higher than 1. It's not the derivative,
Oh,
right? This is notation for the derivative. The first derivative, second derivative, it's in parentheses.
okay.
Just the superscript without parentheses is the D partial sum, right? Where you discard everything degree above D.
Okay.
Yeah, you know, it's kind of unavoidable notational confusion, right? Just
Yeah.
because that's the old notation for derivatives, and you know, like I guess we could make it a subscript, but that technically means something different in some other part of math. So
Yeah.
we just have to suffer. I'm sorry. So Taylor polynomials are strictly more general. They are examples of Taylor polynomials.
I was one of the
Say again.
I was one that like would teach you
It's not. It's just a specific example. Right.
Taylor polynomial is like the concept of like the equations that you plug into.
So a Taylor polynomial you can generate for any function that's differentiable up to the degree that you want the polynomial to be. We're only talking about approximating polynomials for the time being. Right? So Taylor polynomials are defined for any n-time differentiable function. Whereas these partial sums, we call them partial sums because they come directly from the expression of the polynomial, right? We don't have to take derivatives, we can just disregard some of the terms. It's just part of it. Yeah, or you know, I think the common notation in the textbook and what we said yesterday is we use D, right? Up to the D.
Right.
Yeah, but yeah, same concept.
Yeah.
Yeah. Okay. Good. Good. But yeah, I mean, you're right. That is a good observation. That it's the same construction. It's just
Yeah.
specifically
I just
for
saw it by
polynomials.
different names, so I was searching it, like, more general term, I guess.
Yeah.
I was looking for, I was looking back at our example that we used, and we got to the point where this was the answer after we approximated, but then we went back to it and we changed the center and we did much.
Yes. So we haven't finished changing the center. We're midway
Okay.
through that process.
Okay, that's right, but like for, if we got a question for approximation, like that would be the answer.
Yeah. So this is the approximation by the second partial sum. Right?
Our lowest two conference.
That's right. Yep. Okay. So we should start. We'll have the usual here, 40 minutes of lecture and then the last 20 minutes will be the quiz. Yep. Okay, so where were we yesterday? Let me just quickly remind you, we had this polynomial. Oh, this is the worst marker. So we had this polynomial, p of x is equal to, what did we say? 4 minus 2x plus 5x squared plus 9 times x to the 5th. And what we wanted to do is to recenter p of x at x equals 1, which is also not a great marker. So that is to say, we wanted to produce an expression for p of x in the form b naught plus 1 times x minus 1 plus b2 times x minus 1 squared plus b3 times x minus 1 cubed plus b4 times x minus 1 to the 4th plus b5 times x minus 1 to the 5th. And what we did was deduce some general properties of what these coefficients should satisfy by successively differentiating and plugging in x equals 1 to make all the non-constant terms of the successive derivatives go to 0. Right? So let me remind you what we said yesterday. Right? We had p evaluated at 1 is just b naught, right? If I plug in x equals 1 here, all these terms go to 0 and I just get a b naught. Yeah.
This is polynomial approximation.
Yeah, we're still talking about polynomial approximation. Right? This is just picking up the example from yesterday.
Right.
Yeah, good. Okay, so p prime of 1, we just get b1, p double prime of 1. We start to get some additional multiples, right, from the successive differentiation, right, using the power rule over and over again. We bring down powers successively, so we get a 2 when we take the second derivative. Third derivative of p evaluated at 1 turned out to be 3 times 2 times b, 3. The fourth derivative evaluated at 1 is 4 times 3 times 2 times b4. Finally, the fifth derivative evaluated at 1 is equal to 5 times 4 times 3 times 2 times b5. Why do I stop at the fifth derivative?
If you have 5 terms, so if you do anything above it, it'll be 0, right?
Yeah, exactly. The highest degree, the degree of this polynomial p is 5. So after I differentiate 5 times, I'll get 0 forever after that. Also, we only wanted to determine 5 coefficients. We have enough information to do that now. Yes.
Are you just taking the derivative? Like, I don't understand what you're taking the derivative.
Say that again.
I don't understand what you're taking the derivative of, like x minus 1 to the square.
This is what I'm taking the derivative of.
And, right, it's supposed to. So the 3 would come from taking the derivative of.
So let's take the derivative of this expression. So p prime of x is equal to p naught goes to 0, right? That's a constant, times b1 times the derivative of x minus 1, which is just 1, right? Okay, plus the derivative of this term, we have b2. We use the power rule here, times 2, with the chain rule, times 1. 2 b2 times x minus 1. And we continue in this fashion, right? I get more terms, But the point is that each term still has a factor of x minus 1. So when I plug in 1, everything but the constant term disappears. Okay, so now what happens when I take the second derivative? b1 disappears. I get 2 b2. The derivative of this is 1 plus 3 times 2 times b3 times x minus 1 plus more terms that all contain a b1. And then when I evaluate it at 1, when I plug in the 1, I'm just left with the constant term.
We're evaluating p of x like the 4 minus 2x, etc. That's what that's going to be, right?
Nope, I'm just using this expression to derive these. Right, that's why all my answers are in terms of these. I haven't yet applied the original polynomial centered at 0. Right?
This is like you're like making like an equation almost like into that.
Yeah, exactly.
That would still be correct if you were just differentiating the p of x into actual numbers or something.
well, what do you mean by correct?
I mean,
See,
say we were solving that problem, say you wanted to p the x like to whatever.
we'll have to do precisely that in order to set this equal to an actual number, each of these. Right, we'll end up with 6 equations.
I see. Okay, I was just confused because I thought we were doing it for that. I didn't
Right,
really
right.
verify.
Yeah, so again, we're differentiating this expression because all our answers when we evaluate have b terms in.
So we need to plug in there.
Well, now we'll have to differentiate this polynomial in its original form. Okay. Okay. So, where were we? Right. So. Etc. This is an incomplete process, of course. Okay, so. Right. What we have in general is the formula b sub I is equal to the ith derivative of p evaluated at 1 divided by I factorial. Right? 0 factorial, 1 factorial, 2 factorial, 3 factorial, 4 factorial, 5 factorial. Okay, so I'm just solving each of these equations for b. Okay. Yeah.
So p to the I power is being multiplied by 1. What is that?
This is b sub I.
No, I'm saying in the numerator.
Oh, p. This is p differentiated I times, just like this notation here.
And then what's it being multiplied by? What's,
This is being evaluated at 1. Remember, p is a
oh, right.
polynomial.
Yeah, because it's a function.
Exactly. Okay, so this is our general formula for the BIs. If we actually want to get values for them, we have to refer to where our polynomial was originally centered at 0 and do what you were just saying, right? Differentiate the function in this form or the polynomial in this form. Okay, so 1 minus 2x plus 5x squared plus 9 times x to the 5th. Somebody quickly tell me the derivative of this. The derivative.
2 plus 10x plus 45x to the 4th.
Good. What's the second derivative?
And plus 180x cubed.
Cubed, good. Third derivative,
540x squared.
good. Fourth derivative,
1080x.
okay. And the fifth derivative is just 1080. Okay. Rapid pace here. Okay. So now what we want to do is evaluate each of these at 1 and plug it into this formula. Right? Then we'll have actual coefficients b, and we will have succeeded in our goal of writing a new equation for p of x, which is centered at x equals 1. Okay, that was our goal in making this computation. Right, so I've just tried to break it out into a series of steps here. We'll compute the value of all the derivatives of p at 1 using this expression. We deduce a general formula for b sub I. Now we computed all the derivatives in general using this expression where we actually know the coefficients. Now we just have to get everything together and put it in these formulae. You want to ask a question?
What does it mean for it to be centered around a certain number?
It's just what you subtract from x inside the power.
Just like a context for that, or
Is there a what?
like a context like on a graph or something? Does it mean anything on the graph?
So if what I claim is true, that these are equal polynomials, they produce exactly the same graph, right? But the purpose why we do this is so that we can approximate around different points than 0, right? This is centered at 0. We're not subtracting from x anything inside the powers. Right, so that's why we started talking about being able to approximate polynomials near 0. The purpose of recentering is so that we can approximate this polynomial in some small neighborhood around the point x equals 1. Right. So visually, graphically, it has no particular interpretation, but
We're still like,
no, we're not moving. The polynomial, the graph is exactly the same. We're just considering how we can approximate values near a different point.
what is near so far? You say like near, like what is that?
Well, this is like the example that we did yesterday. We look at some small interval. Maybe it'll help if I attempt to draw a picture here. Here's some polynomial, p of x. When we're centered at 0, we know that when we take a small interval around 0, we can approximate well all these points on the graph, right? When we recenter it at 1, using that recentering, we can approximate well at this section around where x is equal 1. Okay. Okay, yep. All right. So let's just calculate all our b coefficients. Again, p evaluated at 1 divided by 0 factorial. Actually calculate the values of p at 1 or the derivative of p at 1 or so on and so forth, I just plug 1 in here, right? So what is my value? So I get 14, 18, 16. 16, what's 0 factorial? 1, good. So now I evaluate the derivative of p at 1 and divide by 1 factorial. So what's the derivative of p evaluated at 1? Get a -2 plus 10 is 8 plus 45 gives me a grand total of 53. What's 1 factorial? 1. And 2. Evaluate the second derivative at 1 divided by 2 factorial. What's the second derivative evaluated at 1?
190.
We get 190 divided by 2, right? 2 factorial. Okay, so what do we get here? This is 95, right? Okay. P3. Evaluate the third derivative at 1. What do we get? 540. Divided by, what's 3 factorial? 6. Good. What does this give us? P3, 90. The fourth derivative of P evaluated at 1 divided by 4 factorial. What do we get? We got 1080, right? Divided by 4 factorial. What is 4 factorial? 24. Good. Which gives us a total of 45. And finally, the fifth derivative of P evaluated at 1 divided by 5 factorial. Well, the fifth derivative is constant, so we get 1080 again in the numerator. Divided by what's 5 factorial? 120. Which just gives us 9. Okay. So here's what you should check now. Um, 4 minus 2x plus 5x squared plus 9 x to the 5th is equal to p of x. And if you actually perform all these multiplications and FOILings, what you'll find is that this equation is equal to 16 plus 53x minus 1 plus 95 times x minus 1 squared plus 90 times x minus 1 to the 3rd plus 45 times x minus 1 to the 4th plus 9 times x minus 1 to the 5th. Again, this is not, this doesn't change anything about the character of the graph of this polynomial. It looks exactly the same because we have this identity, right? But it allows us to approximate near the point x equals 1. And again, near or close is a somewhat ambiguous term because it's up to us to determine how bad the error is depending on how far away from the point we're considering we get. Yeah. Yes.
Could you explain how you got 540 divided by 6?
Yeah, okay, so we evaluated the third derivative at 1, so we get 540. Right? And we then divided by 3 factorial, which is just 1 times 2 times 3. Is this unfamiliar notation, factorial? I was just saying that freely, but I'll just write this down. Call n factorial is equal to 1 times 2 times 3, all the way up to n minus 1 times n. Just the product of the first n positive integers. And by convention, 0 factorial is equal to 1. That's just so certain combinatorial formulas would work out nicely. Doesn't really make sense to say 0 factorial, so we just set it to be 1. Okay. Okay. So right. This is an aside. What can we tell now from having rewritten this polynomial to center it at 1? After recentering, we know that, for example, P1 of X, which is equal to 16 plus 53 times X minus 1, right? So now I'm using this recentered expression to write the first partial sum of P of X. So we know that, for example, P1, and if we would like to take it a step further, we could look at P2. I guess I should really write this on the next line. And P2 of X, which is 16 plus 53 times X minus 1, plus 95 times X minus 1 squared. Our good lower degree approximations of P of X near X equals 1. Right, so maybe this will clear up some confusion. At this stage, when we've just recentered, there's literally no difference between these two representations of the same function, the same polynomial. However, when we start discarding terms, the coefficients are completely different. That's what allows us to approximate well near a different point, right? Contrast with the first and second partial sums of P of X near 0. That is using our original expression, right? This is centered at 0. Okay. For the first, what do we get? We get 4 minus 2x. And for the second, we get 4 minus 2x plus 5x squared. Compare these two polynomials with these two polynomials. These are vastly different from one another. This is what we use to approximate P near 1. This or this, or we could go higher if we wanted to. And these are what we use to approximate P near 0. Again, it's kind of a judgment call as to what you're closest to. You know, depends on how good you want your approximation. Yeah.
Are those the first and second thing? Are those derivatives?
No, first and second partial sums of P of X, right?
So like the first, you're only including the first terms, and the second, you include the second terms.
Yeah, remember the D partial sum is you take all the terms of degree D or less in the polynomial and throw everything else away. That's the definition we had yesterday.
So if you were trying to approximate at 1, what would you plug in for x? Would you plug in like 1.9?
Well,
Or would you flip 6 0?
Well, so this depends, right? This is what I was just saying. This is kind of a judgment call on your part. What is closer to 1.9, 1 or 0?
Oh, so
What's closer to 1.9? Or sorry, what is 1.9 closer to, 1 or 0? So yeah, we'd probably get a better approximation. So yeah, this is why this was so easy to compute by hand is because evaluating this polynomial at 1, which we did over here, evaluating this polynomial and all its derivatives at 1 is pretty easy, right? Because taking successive powers of 1 is just 1. So when you're actually trying to compute an approximation of something, the best thing to do is choose something closest to the point that you want to approximate that's easy to compute multiple powers of. Okay? That's why being centered at 0 is really nice. You're just going to get the constant term for each derivative. Yeah. Okay. Yes.
Little question. So is the notation for the first partial sum the same as the notation for the first derivative?
No. Note carefully. There are parentheses around the superscript when you take the
Like on
derivative.
the first derivative, there's no parentheses.
That's a so p prime of x is not equal to p1 of x.
Alright.
Yeah, that's most definitely my fault. I'll try to be more intentional slanting a prime.
I don't even know what it is.
Sorry. Okay, I should maybe make this more clear. First derivative. First partial sum. Okay. Good. So, let's state this in general, right? What do we do when we want to recenter a polynomial at an arbitrary value a? It's basically the same formula. Okay. So let's let p of x be a polynomial of degree n, and a fixed real number, then there is a unique polynomial q of x of degree n with q of x equal to a sum from k equals 0 to n of b sub k times x minus a raised to the k power centered at a with p of x equal to q of x. And furthermore, the coefficients of q of x are given by a formula. B sub k is just what we wrote along the way in computing our example. The kth derivative of p evaluated at a divided by k factorial. Okay. So I'm going to ask you to take a couple minutes and work out an example, and then we'll talk about it in great detail, and then we'll take the quiz. All right. let me ask you to rewrite the polynomial. P of x is equal to x minus 2 cubed as a polynomial centered at x equals -1. And I'll ask you to use the second partial sum to approximate P evaluated at -0.9. Okay. So why don't we take just a couple minutes, 3 or 4, see what you can do with this, and then we'll talk about how to address it. Okay, don't worry if you didn't finish, that's fine, but let's walk through this together. So you tell me what to do. What's the first thing that we should do in this situation? Yeah.
Do you start with taking, or you said P of -1 to the B initial plus P, you take like derivatives, right?
Yeah. So the reason that we went through the example in the order that we did is so that we could deduce this formula. Right? If I had just started taking derivatives, it's like, why are we doing this?
Mhm.
But because we started by realizing like, oh, when I evaluate P in this new form with the unknown coefficients, I get 1. Or, I get the coefficients back when I evaluate at 1. But now that we know that, we can just start by taking derivatives, right? We'll just take all the derivatives of the given expression for P that we need. Yeah, which is until it turns to 0. Okay, so first, take derivatives. Okay, so what's the first derivative of P of X?
3 times x minus 2 squared.
X minus 2 squared. Good. How about the second derivative?
6, 6 minus 2.
Yep, 6 x minus 2. Third derivative?
6.
Yep, we just get the constant term. 6. And I can stop here because every derivative after this will be 0, right? Okay, good. What's my next step? Remember, my goal is to write new coefficients in this form.
Like -1 into those
Yeah.
expressions and put it over the same factorial.
Yeah, exactly. We'll evaluate all of our derivatives at our new center.
I
-1.
have a question.
Yes.
So like the lengthy problem that we just did with the 4 minus 2x was that like, what, were we just trying to prove that formula? Or were we just
Yeah,
a
and
long way to get there?
well, yeah, I wanted to justify where this formula comes from to you. That's why it took, we took a longer route so that we could, I'm not just pulling this out of thin air and saying that this is true, right?
Okay.
That was the intention. I hope that came across. Okay, so let's evaluate our derivatives at -1. But remember, we start with the 0th derivative, i.e. the function P itself. Right? So P at -1, what do I get when I evaluate P at -1?
P1.
Uh,
Oh,
-27.
-27, yeah. -27, okay. P prime at -1. Sorry, slanty. P prime, -1. What do we get? Yeah, positive 27, good. Right, because we get a negative squared times 3. Okay, second derivative at -1 is -18, good. And third derivative of -1, since we're a constant, is just 6. So this tells us right away what our values of B is. B are, sorry. So I get -27 divided by 0 factorial, or -27. -27 divided by 1 factorial. I'm sorry, this is a positive 27 divided by 1 factorial is 27. B2 is -18 divided by 2 factorial gives us a -9. And B3, 6 divided by 3 factorial, or just 1. Okay, now we have all our information to write a recentered version of P with the center -1.
Should we always do the one, the center at 0 first? I just went straight into doing the plugging in 0.9 and having it be like x minus 1.
So if you do that, then your approximation will be worse because you're centered at 0, right? It depends on the format that, I'm sorry, you're centered here at 2, right?
I'm just like, so I'm like plugging in negative 0.9 and doing it, and still centering it at whatever is told in the problem. So x minus 1 is 2.
I'm sorry, so Where are you plugging in 0.9, negative 0.9?
Into X. But I'm doing it like X minus, or in this case, +1, because we're centering it at -1.
So you want to develop an expression for a polynomial centered at -1 before you start plugging in the value you're trying to approximate. Okay. Because you plug in before that, you're going to use a polynomial that's not centered at -1. Right? We haven't yet written down the polynomial centered at -1. So our approximation will be not good near -1. Okay. So let us write down this expression q of x. So this implies that q of x is equal to what are the zero term, -27 plus 27 times x. My center is -1. What do I write here? X plus 1, good. Okay, minus 9 times x plus 1 squared plus x plus 1 cubed, which if you feel like it, you can actually do all the arithmetic necessary here to show that this is equal to our original p of x. Okay, so now, yes,
You might have been about to answer my question, but is that what we use to approximate E of -0.9?
okay, now we have to go back to the problem. And we're told to use the second partial sum of the recentered polynomial, meaning that we will discard everything of degree higher than 2 in this polynomial, i.e. the cube term. Yes,
What would you do if it told you to use the D?
well, they would give you a specific value of d
Okay.
so that you could actually compute a specific partial sum.
Why for B3, why is the 6 divided by 3 factorial?
Well, what's 3 factorial? It's 3 times 2 times 1. Yeah, it's the product of all the positive integers up to what you're taking the factorial on. So yeah. Yeah. Okay. So we want Q2. Sorry, Q2 superscript of x is equal to -27 plus 27 x plus 1 minus 9 times x plus 1 squared. Now we are finally in a position to do what the problem asks us to do. We'll now plug in -0.9 into this expression, Q2. Okay. So Q2 of -0.9 is equal to here -27 plus 27 times what's -0.9 plus 1? Yeah, 0.1 minus 9 times 0.1 squared. If I do a little arithmetic here, what do I get? I get -24.39. This is my approximation of the value of P if I plugged in -0.9 into P. Compare P evaluated at -0.9. What does this give me? Plug this in a calculator if you like. -24.389. So the approximation is pretty good. Yeah. Right. So the approximation is really bad if you don't recenter it.
Yeah, the difference was that instead of doing like ×27, which is just the root at -1, I plug in 0.9 for total.
Right, so that's the whole game, that we're changing the coefficients, and that makes the approximation better near a point.
Should I do that first, just with the, where I say it? Where the problem is.
Yep, exactly. Okay, I think we're ready for the quiz. Same story as last time, please put your name on it.
We need a calculator.
You don't need a calculator. Um, I don't know. It was really up to you.
No, so. Oh, well.
Take one more back there. Yep. That's 10 minutes down. Just 2 minutes left. All right, that'll be time. Please stop working. Have a great weekend. See you all on Monday. Please stop working. Don't make me have to give people zeros. I hate that. And I don't want that to make that a policy, but. Yeah, maybe. Yeah, thanks. All right, great. I like that.
Thank you.
Yeah, you can.
Thank you. Have a good week.
Yeah, you can.